Hey guys, welcome to the fourth video in the Simply AI series. Today, we will be introducing reasoning. We will look at what is reasoning and why you need it, how reasoning works, and an overview of reasoning systems. The main purpose is to introduce the names, big ideas, and provide a glimpse of some details. It's okay if you don't understand some of these details, as we'll cover the important details along with some concrete examples and applications later on. As you can see, reasoning systems is a very different field of artificial intelligence than machine learning. This field has been one of the oldest and has its roots in mathematics and logic dating back to Aristotle and earlier. With machine learning, you fed a very large number of samples to the machine and the machine learned patterns from it. That means if you go to such a machine and query about something that it has not seen earlier, you're not likely to get an intelligent answer. Some say machine learning does not have common sense. Of course, no pun intended. Now, what is common sense? It is sense about some basic facts and rules known to be universally true and the ability to apply them to different situations. Although this sounds simplistic, in reality, that is a very hard thing to achieve, and we can't just let statistical learning models bail us out here. Even if we have never seen something, very often we're able to make an educated guess. For example, even if you have never thrown your smartphone out of a window, you know what happens when you do that. You do not need a million images with labels to make you understand that you should not attempt something like that. Reasoning systems generate conclusions from available knowledge using logic. Such a system needs a knowledge base and rules of logic, and the system is able to draw new inferences by reasoning. In short, what is missing here? Training. What replaces this training? Logic and a knowledge base. Consider a system that has a knowledge base with a commonly known fact: horses can run. Now the system comes across an image of a horse named Seabiscuit standing in a stable. With machine learning, the only thing we can infer is Seabiscuit is a horse. Add reasoning, and we can infer that Seabiscuit can run. When new facts become known, a reasoning system can infer additional facts. Let us say we come to know that a winner runs fast, and Seabiscuit is a winner. Now the reasoning system can infer something new. Seabiscuit runs fast. The amount of information and training needed to draw this new inference is negligible compared to what is needed for machine learning. So what I want to emphasize is that you need to use the right tool for the right job. So now you might be wondering, if reasoning is so useful, how come we do not see it in many AI applications? Actually, it is used very heavily everywhere. Software uses logic, and you can't really do that without some type of reasoning. In fact, since the 1980s, special-purpose expert systems have been in use in many domains. With advances in machine learning, it is projected that the next stage of the AI evolution may have some combination of automated reasoning and machine learning. Let us gain a high-level understanding of the fundamentals of logic reasoning: deduction and induction. There are two important types of reasoning: deductive reasoning and inductive reasoning. In deductive reasoning, one or more statements or premises leads to a conclusion. For example, if we have two premises, humans are mortal and John is human, you can deduce that John is mortal. Two fundamental rules of logic are at play in deductive reasoning. The first one is called modus ponens, which is Latin for method of putting by placing. It states that if we know a rule that states P implies Q, and if there's a fact that states P is true, then Q must also be true. For example, if today is Monday, then we meet for AI. Today is Monday. Therefore, we meet for AI. The second one is called modus tollens, which is Latin for method of removing by taking away. It states that if we know a rule stating that P implies Q, and if there's a fact that states Q is not true, then P is also not true. For example, if today is Monday, then we meet for AI. Today, we do not meet for AI. Therefore, today is not Monday. There are two popular methods of interfacing with deductive reasoning. Consider a very simple example. We have a fact that states Rocky is a frog, and a rule that states that if X is a frog, then X is green. And our goal is to prove that Rocky is green. The if part is called the rule's antecedent, and the then part is called the rule's consequent. The first method is forward chaining, where facts and rules are chained to deduce new facts until you can deduce the goal. For our example, we have the fact that Rocky is a frog and the rule's antecedent that X is a frog. So we can substitute X for Rocky in this rule. Then we can go forward along this rule to its consequent that would now state that Rocky is green. This is our goal, so we forward chain successfully from the facts to our goal using one or more rules. With bigger knowledge bases, we may have to go forward with multiple such rules to reach our goal. The second method is backwards chaining, where we work backwards from the goal, apply the rules, and then see what facts are needed. If we find all such facts in our knowledge base, then our goal is satisfied. In our example, our goal is that Rocky is green, and the rule that meets this goal is X equals Rocky. Going backwards along the rule to the antecedent with X equals Rocky, we need a fact that states Rocky is a frog. We already have that as a fact in our knowledge base, and so our goal is considered met by backwards chaining. Another type of reasoning is called inductive reasoning. Here, we use specific data and knowledge from past experiences to make the conclusion. This added knowledge from the past is what induces the reasoning. However, such reasoning may be error-prone, as things from the past do not necessarily mean they're true in the present. For example, if it's sunny outside, and if past experience tells us that it doesn't rain when it's sunny. For this, we can do inductive reasoning with the inference that it won't rain. Note that there's no law that proves that it did not rain when sunny in the past means it cannot rain right now, but it is highly likely that it won't rain. There are many different types of logic and reasoning techniques. Let's cover a few. General logic. In logic, statements are represented symbolically, and we draw correct inferences by applying formal rules of logic. There are different types of logic depending on the expressive power needed for the application. Propositional logic. Each proposition is a symbol that is either true or false. First-order logic uses predicates like age of John, quantifiers like for all and for some, and variables like if X is a frog, then X is green. Second-order logic quantifies over predicates and over sets of variables, for example, for all addresses of X. Expert systems are systems that automate reasoning in specific domains using deductive reasoning. Fuzzy logic uses logic based on degrees of truth. For example, X and Y is equal to the minimum of X and Y, X or Y is equal to the maximum of X and Y, and not X is equal to 1 minus X. Temporal logic uses logic to reason about a timeline, where truth varies with time. Constraint solvers declaratively specify constraints, and the system uses reasoning to find the optimal solution that meets these constraints. Deductive classifiers define your world using a frame language. Using first-order logic, it identifies inconsistencies and gives additional inferences. It can analyze and generate ontologies. Case-based reasoning solves new problems using solutions of similar old problems. Procedural reasoning uses belief, desire, intention model, where an agent interleaves a partial plan and its actions based on its belief about the current state and the desire as per its goal. Theorem provers use automated reasoning to prove math theorems and verify their correctness for integrated circuits, software programs, engineering designs, and more. So today we looked at what is reasoning, how it is different from machine learning, and highlighted some prominent fields under reasoning systems. Thank you very much for listening to this video, and I hope you join us for the next video where we talk about some more prominent fields of artificial intelligence. See you then!